So today I'm reading paper Decision-Theoretic Approach to A/B Testing. It's from eBay with Stanford University. My idea is to give some sort of better way of choosing a p-value when you are doing your A/B test, not just simply choose 5% acceptance of basically declining the null hypothesis, but having some sort of more sophisticated approach, and they call it decision theoretic approach here. So the abstract is A/B testing is ubiquitous within machine learning and data science operations of internet companies. Generically, the idea is to perform statistical tests of the hypothesis that a new feature is better than the existing platform. For example, it results in higher revenue. If the p-value for the test is below some predefined threshold, often 0.05, the new feature is implemented. The difficulty of choosing an appropriate threshold has been noted before, particularly because the dependent tests are often done sequentially, leading to some to propose control of false discovery rate, FDR, rather than use of a single universal threshold. However, it is still necessary to make an arbitrary choice of the level at which to control FDR. Here we suggest a decision-theoretic approach to determining whether to adopt new feature, which enables automated selection of appropriate threshold. Our method is the basic ingredients of any decision-theoretic problem: a loss function, action space, a notion of optimality for which we choose Bayes and risk. However, the loss function and the action space differ from the typical choices made in the literature, which has focused on theory of point estimation. We give some basic results for Bayes optimal thresholding rules for the feature adoption and decision, and give some examples using eBay data. The results suggest that the 0.05 p-value threshold may be too conservative in some settings, but that its widespread use may reflect an ad hoc means of controlling multiplicity in common case of repeatedly testing variants of an experiment when the threshold is not reached. Okay, so instead of point estimation, we give some adoption. Bayes optimal thresholding. Instead of point estimation, they aim for Bayes optimal thresholding. Basic A/B testing problem. In A/B testing, one has proposed new version of a software platform and wants to decide whether or not to ship the new version. The classic way of conceiving this problem is following. We divide users into two groups, a treatment and a control. We then roll out the proposed update and to the treatment group while leaving the control group with the current version. Using the data gathered from this randomized trial, we then ask whether the new version performed better with respect to some metric. For the purposes of grounding the discussion, we assume that this metric is revenue, which at eBay is roughly equivalent to the gross merchandise bought. The literature on A/B testing has considered several aspects of this problem, ranging from sequential testing issues to study of multi-armed bandit that approximately characterize some applications like search engine optimization and page customization, to practical and computational issues. In e-commerce, tests often need to run for several weeks, so it's usually not practical to keep multiple competing versions of the platform active over a period of time in order to pursue and explore an exploit strategy. Accordingly, the traditional A/B testing framework, in which decision is made after a very experiment, is favored. Sequential testing and multi-level hierarchical dependent structure among the experiments are issues in experimentation at eBay, and we return to this in section 5. Traditional or generic view is to treat the feature adoption decision like a one-sided hypothesis testing problem. The relevant hypothesis is the hypothesis 0, current version is better. A very simple setup is to consider this, is to let theta 0 to be revenue per user in the control group and theta 1 the revenue per user in the treatment group. So that delta 100 theta minus theta 0 divided by theta 0 is the lift, the percentage change in revenue relative to the control group. On observing data, x distributed as big F as a function of theta of x conditioned on theta. From the treatment, theta equals theta 0 and the control theta equals theta 1 groups. We use some procedure which we leave abstract to obtain an estimate of delta prime, when then assume that at least approximately delta prime means delta divided by standard SE theta prime is distributed similarly or approximately T of ni, where ni is T distribution with ni degrees of freedom, and SE of delta prime is the standard error, delta hat error of the delta hat, and ni is unknown. Now in testing, T of x equals to delta hat divided by standard error of delta hat. We compute the tail probability under repeated sampling. So the P is, I guess, the probability, or is it, that's the p-value, equals to big P as a function of condition on hypothesis 0, T on x. I guess x is a random variable, so T on x is bigger than T in x sample, one-tailed p-value. We then threshold on p-value at some level, typically at 5%, and decide to ship if the p-value is smaller than the threshold. Okay, so once more, so this T on point X is a error divided by this, divided by standard error of delta hat. Compute tail probability conditioned on. Okay, basically they are saying that if the difference is big enough, we then under the null hypothesis, we decision-theoretic perspective. An alternative way to look at A/B testing is a decision problem rather than inference problem. That is, our primary goal is to validate or invalidate the scientific hypothesis in one, but to maximize the revenue for the company. In decision theory, we have an action space, A, consisting of all of the possible decisions we can make, and a loss function, L theta, L of function of theta and A, which defines what we lose if the true state of nature is theta, and we decide to take action A in this A set. We decide to take action space. For A/B testing, the action space has only two elements, ship or don't ship. The obvious loss function is L function of delta, and A equals to minus A times delta, where A is identity function of shipping, and the one function, is it identity function of shipping and minus delta? So okay, so I guess this delta is the lift, right? And so if we find that the lift revenue per user, the delta is revenue per user, right? That's the lift, and we find that the lift is, the bigger the lift, the bigger the loss under declining new feature. That is, if we choose to ship and the true lift is positive, then we gain the lift. Equivalently, we lose the negative of the lift. Otherwise, we lose 0. We just get business as usual, GBM. Note that our decision rule A is something that we do upon observing data. So A equals delta, a function of x, is a map from the sample space into action. We emphasize that the loss function in free is unusual in the literature, which focuses on loss functions like squared error and continuous action space, and thus the results we derive here are somewhat non-standard. Well, so this is interesting. So usually in the literature, they actually have a very different loss functions, so that that may mean that this paper is much more interesting in the practical situations of finding a lift for some sort of businesses where some sort of revenue exists, right? And not when you are trying to when you are trying to gain as much as possible instead of just trying to approximate something. It's very topical for this case. So risk, the risk function of decision rule delta is defined as risk function of theta and delta equals expected value based on theta of loss function function of theta delta on all samples equals a integral over the loss function based on the theta. The expectation of the loss over the sampling distribution of data conditioned on theta. So this is the expectation loss over the sampling distribution of the data conditioned on theta. The risk conditions on theta, the unknown state of nature. Since theta is unknown, we seek the decision rule that performs no matter the true value of theta. There are several ways to formalize this. We focus on the bias risk. But bias risks of a decision rule delta is defined as a prior expectation of the risk. A risk as a function of p and delta equals the expected value of the risk equals the expected value condition on p of expected value condition of on f distribution of the loss function, where of p, where expected value condition on p is a function of f, so integral is the expectation of f with respect to p. A decision rule is considered bias optimal if it minimizes the bias risk. Thus, the bias risk deals with the fact that theta is unknown by weighting the states of nature by our prior beliefs and their plausibility. In the applications that follow, we will take an empirical bias approach where we estimate P from the data. With this basic idea in hand, we can consider the set of all decision rules for A/B testing that correspond to the thresholding and p-value and derive the risk function. Suppose that we have a true lift delta and we define delta P is less than alpha. To simplify calculations, we initially consider a simple version of A/B testing problem where X is a noisy observation. Okay, I'm gonna go faster through these parts. I'm gonna sort of try to go to the conclusion while still giving the most contact picture of the paper. So the last equation here, for example, okay, here. Having defined the risk function, we consider bias risks. Suppose that the lefts are extremely realization of the random label, so that delta E is identically distributed with P. Okay, skip this. Bias risk of thresholding rules. We now return to the class of decision rules that thresholds at beta, a statistic that is distributed according to the location scale family with a risk given in 7. If we knew F in 6 and P in 8, we could optimize the bias risk over beta, determine the bias optimal strategy for deciding whether to ship a proposed update to the platform. In many applications, we are willing to assume that F is T or normal. F is T or normal. This is particularly true if A/B testing in the industry, in A/B testing application industry, where X is typical the normalized difference of means from the two quite large populations. At eBay, a somewhat more sophisticated procedure is to use estimate delete, but estimator is then assumed to be approximately Gaussian for hypothesis testing purpose. Okay, I'm sorry, I got lost a little bit. We could optimize the risk over beta to determine the bias optimal strategy for deciding whether to ship a proposed update to the platform. In many applications, we are willing to assume that F is T or normal. This is particularly true for A/B testing applications in the industry where it is typically normalized difference of means from quite large populations. X is typically the normalized difference of means from quite large populations. Okay. At eBay, a somewhat more sophisticated procedure is used to estimate delete, but the estimator is then assumed to be approximately Gaussian for hypothesis testing purposes. We make the assumption here. We then model the true lifts as a student T with unknown location, me, scale T, the degrees of freedom, okay. Which we take down. Okay, there is student distribution. So historical lifts, historical standard errors. Figure 1, left histogram of historical lifts, right histogram of standard errors. Historical lifts. So that there is a graph of historical lifts. It seems to be, I guess, the student or very, it's more of a student distribution. So it plots delta, the lift, compared to the counts, basically histogram. On the right, the historical standard errors count. The sigma y is plotted against the count, again histogram. Left histogram of historical lifts, right histogram of standard errors. We fit the model using Markov chain Monte Carlo implemented in Stan environment with RStan package for R, the data xi sigma I for I historical lift estimates and corresponding standard errors from A/B test performed at eBay during the year 2006. The histograms of xi and sigma I are shown to the top center panel of figure 1. Xi are centered near zero. Distribution is apparently symmetric, but the tails are considerably heavier than the Gaussian. The distribution of standard errors has mode of approximately 0.3, with some values as large as 2. A QQ plot of the empirical quantiles of xi versus the fitted quantile in model 9 with are shown in figure 2. Okay, figure 2, QQ plot of empirical quantiles of xi against fitted quantiles of the model with delta I identical distributed as the student distribution 2.35 of two values. So we see from the QQ plot that we see this sort of linear distribution very thinly aligned around this linear line. So that would mean that the QQ plot is showing that the two distributions are very close. So one of them is empirical quantiles. It's plotted empirical quantiles against the fitted quantiles. Plot for free optimal beta, which we do know for the testing. Bias risk is negative. Significant bias risk for the decision root is 0. To obtain the value, few bias risks for beta of the model estimated. The vertical red line shows the minimum value of beta of the horizontal line 0. Okay, I'm gonna skip these theoretical results. Considering still the case of loss function in free, the F is a location scale family of distributed function, and CDF, and the frequentist risk is given by 7. cumulative distribution function. F is the location scale family of cumulative distribution function, and the frequentist risk is given by 7. We now derive, okay, where is the frequentist risk? 7. Okay, it's somewhere else. This covers the examples in the previous section. This is the most common type of derived and implied setting. We have following general results. Suppose F is a distribution function location scale family with a density of F that is symmetric about the location, and P is density of location scale family and symmetric about the location. Proof we have. So theorem is following result. Suppose F is a distribution function of a location scale family with a density F that is symmetric about the location. P is density of a location scale family also symmetric about the location. Then if expectation condition on P delta equals 0, beta is a critical point of bias. Beta 0 is a critical point of bias risk. I'm gonna skip this one. Term 2, suppose the F is Gaussian and P is density of normal distribution to the random variable, then it minimizes the risk. Alright. I'm gonna go to conclusion. I ran out of time. Discussion. Traditional A/B testing has treated the decision of whether to shape a feature as a hypothesis test, requiring research and development teams to make an arbitrary choice of p-value threshold at which to adopt new feature. The decision-theoretic approach we outline here has potential to automate this choice by using the data of previous tests to inform about an optimal threshold via Bayes analysis. We have not considered here the case where the modification to feature affect the lift. Though we find some evidence of small average improvements due to modifications at eBay. Extending the decision-theoretic analysis of the optimal thresholds to this more complicated setting is an interesting extension of the current work. Okay, that's all, folks. Thank you for listening. See you later.